Hello everyone, thank you for joining the session. My name is Aliaksei Sala, I am lead software engineer at EPAM Systems, and today I will tell you how I try to achieve the peak performance for matrix multiplication using C++. So why matrix multiplication? I find this use case really useful to be able to demonstrate different optimization techniques. And the second reason, it's one of the most fundamental computer science operation. If you are modeling scientific simulations, transforming 3D models in computer graphics, training machine learning models, you are executing matrix multiplication under the hood. And it's just a tip of the iceberg. There are so many different areas where the matrix multiplication is used, such as self-driving cars, robotics, financial modeling, etc. And why do we need peak performance? And I think the reason for that, because it enables us to invent new technologies. At that table, we can see AI breakthroughs people made in the past 15 years. And we can notice how the computing requirements grows over time. According to OpenAI data, computing required for training new model double every 4 months. So achieving the peak performance is really important. And matrix multiplication itself is so important that the companies start building hardware around that operation. You probably heard about tensor processor units from Google or tensor cores in your video card. All of this are basically hardware implementation of matrix multiplication. And on that chart, we can see how the performance of the single chip increased in the past 10 years. On that plot, we can see theoretical performance. And to be able to achieve it, we need to know how the hardware implements under the hood. And this raises a concept such as hardware-software co-design. So software, people who write software must know how hardware implemented, and hardware folks also should know basically what software people, which kind of operation they use. So nowadays, hardware-software co-design become more popular. And in that talk, I will try to ask, can we leverage the full capabilities of CPU while staying within the bounds of standard C++? And a little bit background context. So I assume that we are familiar with some hardware fundamentals like CMD operations, cache memory. And if you are not, I will stay a little bit and introduce these concepts in the future. In my case, matrix is just a vector of doubles aligned on CPU cache line. In my case, 64 bytes. Elements are stored in row major order, and I will do the dense matrix multiplication of square matrices with fixed dimension. And I choose the dimension which is bigger than last level cache on my CPU. And the flows of the session will be the following. I will show you C++ implementation. Then we evaluate the performance. And to be able to do that, I used Google Benchmark. All benchmark run on Linux operation system, use the Intel CPU with Haswell microarchitecture, and all code compiled with the following flags. You can see on that slide. Then we review the results and proceed to the next optimization. And before we start, let me introduce what does it mean peak performance for my particular presentation. So the way how I compute it, I take number of cores in my CPU, multiply by base frequency, and multiply by floating point operation per cycles, which my CPU can do. So in that particular case, my CPU has 4 cores, 2.3 GHz base clock, and the multiplier 8 comes from vectorization, and multiplier 2 comes from instruction throughput. So basically, my CPU can execute 2 CMD instructions at a time. So we have like our theoretical performance 147.2 gigaflops. And let's start with the naive matrix multiplication. So naive matrix multiplication can be implemented like that. We have triple loops which iterate over I, j, k indices. And we basically take every row from matrix A and element-wise multiply by every column of matrix B, and the result add to the element of C. And it's pretty straightforward implementation. And let's measure the execution time. We can see that it takes like 152 seconds. On that table, I will add all implementations with different optimization techniques, so we can compare relative speedup. Relative speedup will show you the current implementation compared to the previous one. Absolute speedup will show you the comparison of the current implementation with the naive implementation. And gigaflops columns show us the number, how many gigaflops this specific implementation takes, and the percent of peak performance. And how I calculated peak performance I'll show you in the previous slides. The next optimization is changing loop order. So instead of iterating over I, j, and k indices, we can switch, for example, j and k loops. So why do we want to do that? And the reason for that, data access pattern. If we check our initial implementation when we iterate over I, j, and k indices, we can notice that we iterate over A elements sequentially, which have good spatial locality property, and it's really efficient. But when we iterate over elements from matrix B, we iterate over like a huge stride, since our matrices has huge sizes, like which cannot be fit into L3 cache. And this data access pattern have a bad spatial locality property and it's kind of slow. Another reason for that, when we read element, we actually read not just one element, but several of them to fit the whole cache line. And if we take elements with the huge stride, we basically don't use all elements which we fit into the cache line. Another reason for that with the huge strides, hardware prefetcher also works pretty badly. So we would like to have good spatial locality and sequential access for our elements. And when we change the loop order, now we can see that we sequentially access elements from matrix C and B, and we reuse element from matrix A. And this optimization gives us 12.6 speed up compared to the naive implementation, which is the biggest one. Next optimization is tiling. So let's imagine that instead of multiplying elements, we will multiply blocks. And by blocks, I mean we basically split our matrices into the block sizes, and each block will contain some elements from matrices. And our implementation first iterate over different blocks, and when we pick, for example, the specific block of matrix C, A, and B, we will execute the element-wise multiplication. So in that case, for example, when we compute let's say elements within the specific block, we, for example, take elements from the row of the first block, multiply by several elements of the B matrix. Then we take next elements from the B matrix to compute the next C element. Then we reuse the elements of B by take the next row of elements of A, and reuse the elements of B to compute the next element of C. So in that case, we calculate the all elements from block C and reuse elements from block A and B several times. The way how it affects the implementation is the following. Instead of iterating over I, J, and K, now we iterate over our blocks with the fixed size. And within each blocks, we have inner loops which do the element-wise multiplication. And this function I will call kernel here in the next slides. And we will move it to the separate function. The Tagging optimization tripled the performance compared to the previous implementation. The next optimization we can apply is vectorization. A few words about vectorization. So if, for example, we need to add few elements from array A with few elements from array B, we basically, for example, if we have 4 elements, we need to execute 4 operations. For CMD, it's single instruction, multiple data. We actually don't use element, but we use special vector registers, and we can execute only 1 operation to get the same results. And before we start vectorize our implementation, let's check what compiler generates for us. And we can see that compiler actually vectorized our matrix multiplication. And even more, when we move our most inner loops to the kernel function, it generates even better assembly code. The reason for that is now we use more CPU registers compared to the previous implementation. But let's try to vectorize manually and see what it gives us. So this is how the vectorized implementation looks like. And the first time I saw that implementation in article What Every Programmer Should Know About Memory, written by Ulrich Draper. Highly recommend to read. It's quite old, but still it's still very useful. This implementation uses 128 bits instruction and registers. My CPU supports 256, so I updated the initial implementation a little bit of the kernel. And the way how it works, we take the element from matrix A and then broadcast it to the vector register. Then we take few elements from matrix B and move it to the vector register B. Then we load the elements from register C, from matrix C to the C register, and execute our CMD instruction, which is called FMA, or fuse multiply add. So it's basically do the job for us, multiply elements from matrix A and B, and put the result into the register C. And the result, we move back to our matrix C. So basically, this is how our matrix multiplication kernel works, vectorized one. And if we compare after vectorization with manual vectorization, we can see that the assembly code looks pretty different. We don't need to read it, but what I would like to highlight, that after vectorization doesn't utilize all available CPU registers compared to the manual implementation. And if we compare the results, we see that we have 1.23 speed up compared to the previous implementation. So the next optimization is cache-aware implementation. And before I show you the implementation, let's briefly review the memory hierarchy. So on the top of the pyramid, we have CPU registers. It's the most performance, the most expensive, smallest memory we have. And on the bottom of the pyramid, we have hard disk, the biggest, the slowest memory on our machine. And this is the image created by Robert Van de Geen, who is professor of computer science at University of Texas, which helped me to explain how we can utilize memory hierarchy to implement the cache-aware implementation. So if we review the first loop around microkernel, we can notice that we iterate over I index. B matrix does not depend on I index, so that means we basically multiply one block of B by several blocks of matrix A. So since we are reusing the block of B, this is the most frequently accessed memory. And the most frequently accessed memory we would like to put into L1 cache. Knowing the size of L1 cache, we could estimate the size of the block B. If we have a look on the second loop around microkernel, we can see that here we iterating over J index. And now our A matrix does not depend on J index, and we reuse elements from matrix A. The same logic applies. We would like to put all of these elements into L2 cache. And knowing the size of the L2 cache, we can estimate the size of the block of the matrix A. This is our initial tiled implementation, and the way how cache-aware implementation impacts that we don't use the fixed block size anymore, and instead we have a little bit more loops. Now we have cache blocks and register blocks, and all blocks have different sizes, depends on the dimension. So some denotes. So NC, MC, and CASI are used to denote the cache blocks, and subscript C means cache, and NR, MR means the size of the register blocks, which basically we use the tiling optimization, but now we split cache blocks into several blocks. And R denotes the register. And our previous kernel also little bit will be changed. Instead of fixed block size, now we use pre-computed block sizes for register blocks. And after implementing cache-aware implementation, I noticed that the compiler no longer utilizes all available registers. So basically, assembly became worse than previous implementation. And current implementation utilizes only 4 out of 16 available registers. Even though we get 1.16 relative speed up compared to previous implementation. But let's help compiler to use all available registers. So the way how I try to do that, I try to hint to the compiler how many CPU registers we have on my machine. And the way how I did it, so mental model. I have 16 register total. So I would like to allocate 12 registers for C elements, 3 registers for B elements, and 1 register for A elements. And for this particular case, I just provided only one constant, which is called C register CNT. And in our case, it will be 12. And the most inner loop I and G, compiler automatically unrolled and deduce amount of registers for B and A elements. And if we compare the output assembly, we can see that now we use all available registers. In the previous implementation, we use only 4. Now we use all available registers. And a register-aware implementation gives us 1.92 relative speed up compared to previous implementation. The next optimization is multi-threading. I tried different approaches, tried to parallelize multiple loops on the, nested loops. I tried to pin specific thread to specific core. That didn't give me any meaningful results. So for that particular case, like our model is pretty simple. We just split our matrix C into the 4 equal sizes and parallelize only the outermost index. And it tripled the performance compared to the previous implementation for 4 cores CPU. The next optimization is stride. So the one thing I noticed that when we iterate within the kernel implementation, we use the huge stride for matrix A and B. And the stride basically equal to the size of the one of the dimension of the matrix, which is really huge. So the first idea comes, okay, how we can reduce the stride. We can basically take our cache block and move it to the buffer. And when we do that, instead of striding with the n size, we are now reduce it to the nc, which equal to the cache block size. And instead of striding with the value of n, now our stride equal to nc. And the same trick doesn't work with matrix A. So packing matrix A to the buffer had no impact. And this packing of matrix B speed up the implementation by 1.17 times. Matrix style layout, the next optimization. So I reduced the stride a little bit, but it's still huge. And when I measure different stride sizes, I noticed that from some level it stopped working. So our goal is to minimize stride as possible. And can we make stride equal to 1? And actually we can. If we take a look how we are iterating elements over the matrix, the pattern looks like that. And I already basically copy the block of matrix to the buffer. So I decided, okay, I don't copy element to the buffer, just like we do with submatrices, just copy element one by one. But I use this data access pattern to iterate over my matrix and copy them into the buffer. So in the kernel, I will have sequential iteration over elements of the matrix. So during the repacking, we have this basically tile layout data access pattern, but during the computation of the block of the matrix, we iterate elements sequentially. And the way how it affects our kernel implementation is the following. Now, instead of iterating over size of the cache blocks, we are iterating over register blocks. And these numbers are pretty low, and r equals to 12 and r equals to 4. But compiler will unroll innermost loops, and basically the stride will be equal to 1. And here we see that we don't have any more loops and basically iterate elements sequentially. And it gives us 1.1 performance improvement. In C++, we will have std.cmd. And I was really surprised how easy it can be used even right now. So instead of using these intrinsic functions, I just replace all these intrinsic functions and registers to the simd type and use regular multiplication and addition. And it just works. And we all know that C++ basically a language with zero overhead, so it doesn't affect the performance. We have the same performance with CMD library. The next optimization is loop unrolling. I already showed you that the compiler already unrolled innermost loops. But what happens if we do that manually? Let's try and see. So we start with our innermost loops. And what we should do basically, we just need to remove the loops and rewrite all of this operation manually, like 12 multiply 4 times. But in C++, we can kind of generate that code. And to be able to do that, we can use pack plus fold expression and built-in comma operator. And the idea behind it is the following. Let's just take as an example the simple test case. For example, we have a print function. We need to call it 4 times. with indexes 1, 0, 1, 2, and 3. So instead of calling one function 4 times, we can implement a function with the name call print end times. And this is how we use fold expression over comma operator to generate our print 4 times with indices 0, 1, 2, 3. And if we don't want to pass all of these arguments manually, like if we have, for example, not 3 elements but much more, we can use some helpers, which calls make index sequence, where we put the number of elements we wanted to generate. And make index sequence is basically template alias to the make integer sequence, which basically generate our sequence from 0 to n-1. So this is how we can generate code, and let's apply these techniques and generate our matrix multiplication kernel. So the kernel will look like that. We use our JPAC to generate several B registers. Then we use pack of I to generate several functions which I called compute row. And our compute row basically generate several multiplication of elements A and B. So it's basically equivalent code. And our compute kernel looks a little bit wordy, so we can wrap up this compute kernel with rename it to compute kernel implementation, for example, and hide all of this implementation details inside the compute kernel function. And the final result looks like that, which a little bit cleaner. And let's use our manually unroll kernel here. And the same technique we will use to generate load inc store operations. It's basically when we update element of matrix C with the result we already computed for for our block. The idea is the same. We generate load inc store double functions 3 times in our case using the IPAC. And we have a function store kernel which generates several functions of store row. And we have a function which stores the result into the matrix C. And the full implementation of our kernel will look like that, which applies the loop unrolling. And let's compare the result. On the left-hand side, we see after unrolling version. On the right-hand side, manual unrolling. And the only difference is where compiler put the one instruction, which is called broadcast. On the left-hand side, we start the loop with this instruction. On the right-hand side, it moves after the move up operations. And let's measure the performance. And we can see that we slightly improved it. So basically, this is one of the examples. We all know that compiler can reorder the instruction, hardware can reorder the instruction, but this is the case where we can see how the compiler does it in some cases. And it's really matter instruction order, but from C++, it's really hard to impact on that. Another optimization is prefetching. This is one of the most harder one. So basically in CPU we have a hardware prefetcher, which we already try to utilize when we have the sequential access. But hardware prefetcher also have some limitations. One of them, for example, it doesn't work across page boundaries. And if we know that we're definitely gonna use some data in the future, we can prefetch this data from RAM memory to the cache in advance. And this is the CPU instruction. It takes time to execute. That is why it's super hard, at least in my case, to apply it correctly, because most of the time it could even hurt the performance. So what I found that prefetching elements from matrix C almost always lead to the better results. And I'm still kind of experimenting with the prefetching, and the best result I got give me the 1.7 improvement speed up compared to the previous implementation. And we can see that we reach like 96.6% of the peak performance, which is really good. And to be able to see if it's possible to do better, I used OpenBlast implementation, and OpenBlast gave me 104% of peak performance. The reason why it's bigger than 100% is because when I initially calculate the peak performance, I use the base frequency 2.3 gigahertz, but when I try to fix the frequency during the test, I only managed to do that with 2.7 gigahertz. So this is the reason why we have a little bit higher numbers for the OpenBlast implementation. But we see that there is some room for improvements. So why it's hard to reason about the code performance? And there is no points in analyzing C++ code. So most of the time I check the assembly which I got. And analyzing instruction for slowness doesn't lead to the same conclusion when we analyzing function in C++. So for example, if we see the slow instruction, it not necessarily means that we need to optimize this specific instruction. It could mean that this instruction wastes some data from the memory, and we just need to reorder some data access pattern somewhere else. And it's super hard to utilize the instruction level parallelism. And here we trust the compiler it ordered the instruction in the best way possible, but it's not always the case. Another interesting example I found in the internet, that one guy renamed the register. So instead of using RCX, he started using ECX register, and it improved the performance. And the reason why it helps, because Haswell microarchitecture had a bug, hardware bug, which disabled the register renaming optimization on the CPU level. But when you rename the register, with this particular register, hardware able to use the register renaming optimization. And we cannot do such fixes from the CPU or from C++. And a little bit about numbers. When I measured performance, I used vtune utility to check numbers and perf. So this is the result of the vtune, and we can see that my implementation on the left-hand side has some memory bounds, core bounds issues, and it's a little bit worse compared to the OpenBlast implementation. And when we check the perf stat, it's not so obvious anymore, because my implementation utilizes caches better, but it doesn't lead to the conclusion that my performance, that my execution time is lower. So some of the metrics better on my implementation, some metrics better on OpenBlast implementation, like instruction per cycle, for example. And what this number tells us. So when we almost reach the peak performance, the reasoning, like regular reasoning, stopped working, because on the left-hand side, the implementation we measure, and I show you the result in the table. On the right-hand side, I manually unrolled another loop. So we basically don't have any bottlenecks anymore, like compared to the left-hand side image where we have a bunch of red instructions, but the execution time exactly the same. Moreover, on the left-hand side, we have an implementation which have all metrics better than the implementation on the right-hand side. But on the right-hand side, we have an open BLAS. On the left-hand side, we have an implementation which utilizes 180 28-bit instruction and registers. It's much slower, but VTune shows us much better numbers. And cache utilization also doesn't lead to the conclusion that the implementation should perform better. So how effective is C++ for matrix multiplication? So little bit digress here. All kernels in Open BLAS implementation I check Bliss implementation, all written in assembly kernels. And I can understand people don't want to struggle against the compiler, especially when they want to utilize IPC. They don't want to depend on specific compiler or version, and they want to be able to contribute fixes for adequate period of time. And I refer to the example I showed you with the register renaming. And the performance for various implementations, in my case, vary between like up to 40% between C-Lang and GCC. So basically, I compile the same implementation with different compilers, and for some implementation, performance dramatically changed, but not for final version. But in C++, we have a mature ecosystem. So we have a bunch of libraries which do a pretty good job, like Cocos, BLAS, CUDA, which enables us to execute the code on GPU devices, etc. In C++, we have zero-cost abstraction with templates, const explorer, which helps to write generic readable code that compiles to kinda fast kernels, because even 95% of peak performance, I think, a great result, because compared to the assembly implementation, like you don't need to read 5,000 assembly lines code. It's chip ready, at least what I saw. People use C++ to implement different mass instructions for RISC-V, for TPUs, etc. And we have more power on the horizon. I already show you CMD, but we also have MD-span in the future, reflection, which could help to produce more efficient kernels. We have linear algebra in the standard library, so you don't need to implement matrix multiplication anymore. Executors, which help us to execute code on different devices, etc. And powered by a strong and active community. Even here, I have so many great talks with you guys, learn a lot, so really appreciate. And few alternatives I would like to mention. So we have MLIR. It's a software framework for compiler development. And what it allows compiler developers do to introduce high-level intermediate representation, which custom operations. So you basically could add matrix multiplication to your high-level intermediate representation and compile your triple loop to the matmul. And for that case, for the compiler developers, it will be much easier to produce the efficient matrix multiplication. And I found one project with name PolyJest, which use this approach. And I found the module language, which also applied this approach. It's kind of Python-like language, which allows you to write matrix multiplication, which looks like that, and apply all different techniques like vectorization, split to the tiles, parallelization under the hood. But in my machine, Mojo gives me 70% of peak performance. And another alternative is large language models. It keeps getting better. And the last one also generates me matrix multiplication, which gives me 70% of peak performance. So as we see, there is some still, like, I think it could be done better. I think I'm missing something, so I will try to improve my latest implementation in the future. The most common question is why CPU, why not GPU? I have a plan to repeat the same exercise for GPU and TPU as well. So thank you so much for your attention. And if you have any questions, please feel free to ask.
I could be wrong, but when you had that stride,
Mm-hmm.
And because of the large stride, the address bits for the tag bits of the cache for the addresses could be same, and then the cache has to evict the same tags. That could be the reason for that.
Yes, cache assertivity, it's another thing I would try to do, like deep dive into it, because yeah, if you choose the wrong size of the cache block, you could basically write into the same cache set. So you need to choose carefully the cache block sizes in that case, yes. Any more questions?
It was a nice and interesting talk.
Thank you so much.
It's I mean, it's a complicated. I guess you were working for months until to finish this.
Even more, because it's a pet project.
So I know you like right try, it doesn't work. You try something else.
Yeah.
It's like the end results.
Yes.
Probably something about CPU stuff. You use a very old CPU.
Haswell, it's pretty old one.
It's
yes.
10 years old now.
Yes, even more.
Is this intentional, or you just that's what you had at your disposal?
It's not intentional. This is what I had like a year ago. Now I'm building a new machine. I highly likely I will buy Zen 5 and do the same exercise for Zen 5 microarchitecture.
Can you use AMD 512 with it? Zen 5 supports AVX 500.
Yeah, this is the reason. Yes.
I couldn't find. I bought a Zen 4 laptop. I couldn't find a Zen 5.
I find they available even on Amazon, UX, so plenty of stuff where you can buy.
Who is the producer? Who is the manufacturer?
Oh, don't remember right now. But you can, even on official website, you can find this information, I guess. No?
I found HP ZBook, which was Zen 4, but I couldn't find anything Zen 5.
Interesting.
I'm looking forward to the update of the talk.